In this section, we will explore how the COMxL can be used to solve for constraint optimization problems, the Lagrange multiplier method, and the KKT conditions. So we have our problem statements and we have our function to be minimized to be x1 minus 5 all squared plus x2 minus 4 all squared, subject to the constraints 2x1 plus 3x2 less or equal to 12, 6x1 plus 3x2 less or equal to 18. It says using the Cantucker condition, that is KKT condition, find the values of x1 and x2 that optimizes the objective function. Find the value of the operation cost. So we have our objective function, that is the OC function, in terms of two variables, and it's subjected to two constraints. That means the Lagrange function is going to be of four variables. In here we have variable x1, x2, lambda 1, lambda 2, and the Lagrange function is going to be expressed as this thing over here. So our objective function plus the multiplier with the product of the multiplier and its constraint. So for our first constraint, we have our lambda 1 as a multiplier, lambda 2 for the multiplier of the second constraint. So for the Cantucker conditions, the first derivative of the Lagrange function must be equal to 0. So we get the first derivative of the Lagrange function, but that is the L dx1, the L dx2, the L lambda 1 and the L lambda 2. So we have it over here as this. So we extract the variables of the Lagrange function here, x1, x2, lam1, lam2. The KKT solver in the COMxL works under iterative means, but the user needs to be putting in values for every run, for every iteration. So mine the L dx1, the L dx2, the L d lambda 1, the L d lambda 2. So I specify any values for my first iteration. So my derivative with respect to x1 is 2 times x1 minus 5 plus 2 times lambda 1 plus 6 times lambda 2. The second constraint, that is for our second derivative, 2 times x2 minus 4 plus 3 times lambda 1 plus 3 times lambda 2. And for lambda 1, 2 times x1 plus 3 times x2 minus 12. And for lambda 2, 6 times x1 plus 3 times x2 minus 18. So we have this over here. So I will create a small table. So in the table, I have my x1, x2 values. So x1, x2, lam1, lam2, and my first constraint and my second constraint. Yes. So for the first constraint, it must be less or equal to 12, and our second constraint must be less or equal to 18. So let's make here cons 2, and make here cons 1. So I create my KKT solver. It says select the range of cells that contain Lagrange variables, that is these cells, and you want to select that contain Lagrange derivative, that is these cells. So I run the solver. Now after running the solver under these conditions, we have the value of x1 to be 1.5. So I'll just copy the values in here. x2 is 3, lambda 1 is minus 0.75, lambda 2 is 1 point this. But then, so I can, just before I test it in the constraints, and the KKT condition, the number values must be positive. So seeing this value is negative, it violates the Cantucker condition. So I will leave it as it is. But if you are to test the values of x1 and x2 in the constraints, they satisfy the constraint. So if you have, so for our first constraint is 2x1 plus 3x2. So it's fit the constraint. It's fit constraint 1. Our second constraint is 6x1 plus 3x2. That also fit the constraint. But the lambda 1 value cannot be negative under Kuhn-Tucker condition. So these values of s1 and s2 are not the optimal values, are not the optimal point. It's not optimal point. Now what do? So I switch to the cases. So let's say under case 1, our lambda 2 is 0. Case 1. So let's say our case 1, our lambda 2 value is 0. So I set lambda 2 to 0. Now if lambda 2 is 0, I come in here. So I come into my derivative function. So function this, and this. So in this function, wherever there is the reference to the cell that contains the lambda 2 value, I take that cell out. So if I come to this, the LDX1, it references lambda 2, that is this cell N5. So I take the cell N5 or I set it to 0. In this, it's referring cell N5. I set that cell N5 also to 0. In this, it doesn't reference cell N5. This is with respect to lambda 2 itself. So I will add the cell N5 to it. So plus lambda 2. So whichever variable is set to 0, you add its value to that function that contains a derivative. In here, our lambda 2 is rather 0. So we add its value to the derivative of lambda 2. So I set my starting conditions also to 1. And I run the iteration. That is the solver. So value that contain the values. And derivative. I click on solve. So it has finished solving. So the s1 value for this case is this. The s2 is also this. Our lambda 1 is this. And then since we set our lambda 2 to 0, we will discard this value for lambda 2. So now we have s1 positive, s2 positive. Our lambda 1 in this case is positive. So that is true. But then we have to test it in the constraint. So if you test it in the constraint, our first constraint is fully satisfied. So it satisfies the first constraint. But it violates the second constraint. So our second constraint is violated by here. So that means that at our lambda 2 value of 0, the points for s1 and s2 will not be the optimal point. So now I come to the next case. That is case 2, where I set my lambda 2 value to 0. So I come back into my function. In this case, I will keep the value that refers to lambda 2. And I will set the value that refers to lambda 1 to 0. So that is the cell N4 to 0. So I'll keep this. Now set the one for lambda 1 to 0. And I'll take that which I added to this. And I'll add the cell that refers to lambda 1. So the derivative with respect to lambda 1. Yes. So now I run the next case. So for this case, it says cell x1 value is 1.8, s2 is 2.4. As we said, our lambda 1 was 0, so you discard this 1.2, and lambda 2 is 1.0. Now we have our lambda 2 value of positive, and lambda 1 is 0. That satisfies the Kuhn-Tucker condition for the multipliers. And we have x1, x2. So we check the value of the x1, x2 in the constraints. So I check with this. Sorry. So I check with this and I check with that. So as we can see, when number 1 is 0, x1 will be 1.8, x2 will be 2.4. Now number 2 will be positive 1.06667. And for our first constraint, we get 10.8. That is less than or equal to 12. My second constraint will be 8. That is less than or equal to 12. So at this point, have our optimal point. But what if this is not the optimal point? But this is. But what if it's not? We check the case 3. In the case 3, both lambdas are going to 0. So lambda 1 is 0, lambda 2 is 0. In that case, I will set my lambda 2 again to 0. That is the cell n5. I will set the cell n5 from 0 to 0. And since I have already added the cell for the lambda 1 to the lambda to the vector of lambda 1, I will leave it. And I come and add the cell to this, cell for lambda 2 to this. So I will change my starting point and I'll run the server once more. So here I have s1 to be 5, and I have s2 to be 4. So I take my constraints. So as we can see, it will violate the first constraint and it also violates our second constraint. So this constraint will be violated. So for the last case, that is, if the lambdas are both 0, we will have both violations to the constraints. So this is how to use the COMxL to solve constraint optimization problems with Lagrange multiplier method.